Good morning, everybody. Thank you for logging in. We are going to give it a couple minutes before we get started.
Sharing of screen is disabled by host.
I'm fixing it. 1 second.
Gotcha. Can you hear me, Alex?
Yep, I can hear you.
Oh, cool.
Okay, Lance, you should be able to start sharing.
There we go. Let's see, Microsoft PowerPoint 80 page. Okay. You let me know if you can see full
can see
screen. You do see it?
Yep.
Okay. And I'm trying to get to, I'm going to see if I can move this bar over. The bar is actually blocking my PowerPoint presentation button. I'll do it down here. I'm gonna undo my phone real quick. I just realized I got to put it on airplane mode.
Good morning, everyone. Thanks for joining the call today. We are going to get started in a couple minutes. We're just give it a couple minutes for people to get logged on.
Trying to get full screen here, Alex.
Yep, play from start.
Excuse me?
If you hit the first play from start button, you should be good.
Yeah, that's what I did. And are you seeing the full screen?
No.
Nor am I. Why is it acting different? Oh, here we go. And are you seeing full screen now?
No.
Now let me see what this does. Try this. Come on. Alex, I don't know what's happening here. Why it's doing this. I'm going to try.
Maybe unshare and then share again.
Unshare.
Like stop sharing your screen and then
Stop
reshare.
share. Okay, here we go. Share screen. PowerPoint. I don't know how this got into the picture. Let's play from start. Let me try the PowerPoint. I just as soon not use the I'm sorry.
The PDF.
The PDF, but maybe I'll have to do that. Hello, Tom.
Hello, Lance.
For some reason, I'm not getting full screen on this. We had it yesterday. Didn't change a thing. Let me try. share and XYZ. Let's go with, I'll try PowerPoint one more time.
Good morning, everybody. We're just getting set up and then we are going to get started in just a minute.
Are you seeing full screen now?
I see I think you're sharing. It must be projecting onto a different screen because I see your files.
It is projecting on two screens. I'm going to stop that right now. That's maybe the difference. Let me grab the PowerPoint. That may have been the whole thing. I was going to put it up on the upper screen.
All right, while Lance is getting set up, I'm just going to talk through a few logistics. You please use the chat and Q&A functions at the bottom of your screen to ask any questions or give any comments throughout the presentation. Feel free to comment or send questions at any time and we will try and answer throughout the presentation. If not, we will address at the end. Lance, do you want me to try sharing?
Am I in? I have full screen. Is it okay?
I'm still seeing your files, not
Stop
the.
share because I have full screen. Let me stop share and retry to share again. Share screen. I'm going to.
Yeah, when you open that, we're not seeing that. We're just seeing your file.
Really? Yeah. Do you want to go ahead and put your screen up then?
Sure.
It didn't do that yesterday.
No, didn't.
That's the PDF.
Okay. So you just give me a cue when you want me to move to the next slide.
Okay. I can't do it from here, obviously.
Yep. Nope, I'll do it. I'm actually going to kick it over to Tom to give a few announcements and kick things off and introduce you. Tom, go ahead.
Hello, everybody. First of all, thank you all for participating in today's educational meeting with the Chief Engineers Association. Lance Rock is going to be our presenter from United Building and Energy Services. Little bit of history between Lance Rock and myself. Actually, when I was a chief engineer at 22 West Washington, I worked with Lance Rock to help balance our systems, and it was the fluid side and also the air side on our air handling units, and did a fantastic job. He also is an instructor at Local 399 as well. One of the reasons why we thought it was important that Lance presented today was because of our environment that we're in currently. You as engineers and chief engineers may find it important to know that sooner or later, actually probably sooner rather than later, you're going to have to start to utilize your basis of design and your sequence of operation prints fairly soon, as you're going to have engineers coming into your buildings to try to figure out how to better, I guess, dilute the air that's coming inside your buildings. And when this occurs, you're actually going to see your energy costs rise, and that could be an issue. So it might be beneficial for you all to start to take a look for those prints and be prepared for when that occurs. And Lance here is going to walk you through some of the things to look out for, and even get into some of the math that you might want to become acquainted with. So Lance, thank you very much for participating and presenting today. I do appreciate it. And I'm going to hand it off to you. Okay, Lance?
Thank you, Tom. Can you hear me, Tom?
Yes, perfect.
Okay. And thank you, Alex. I'm going to be saying next because I don't have control of the slides. There's an issue with my presentation, so it's being presented through 399. Thank you for attending. Again, my name is Lance Rock. Next, please. I am the principal inventor of patented HVAC building and infectious disease technologies. What we first did years ago is found a way to be energy optimized on most buildings. I learned the science is testing nuclear power plants using tracer gas technologies, SF6, sulfur oxyfluoride, and hypodermic syringes, literally injecting mixed gases into hypodermic syringes to find dilution. And I found a way to use ambient air. My certifications, next please. My certifications, the acronyms are listed here. You will be getting a copy if you would like of this presentation, but I am a certified energy manager through AEE, Associated Energy Engineers. I'm a CRM, Carbon Reduction Manager, a certified energy auditor, professional energy manager. I'm certified through NEMI. I'm a certified commissioning authority. I'm certified through ABC TBE TAB, which is the Testing and Balancing Bureau through Sheet Metal Workers International Association, LEED, Infrared Analysis 3 through FLIR, and Vibration Analysis Level 1 through NTEC IRD. The patents that I have are literally in regards to reading airflows and mixing properties of, I shouldn't say airflows, of all fluid flows. And our fourth patent we're going to develop is encompassing DX for many reasons. Next, please. Those are the 3 current patents. The numbers are on them, and we're looking to get our fourth as the process goes through. Next, please. I'm currently an instructor for Triton, as Tom mentioned, for Local 399. I also teach at College of DuPage. I'm a certifier for Unibus. The reason I am a certifier for Unibus, the certifications that we provide and the training that we provide cannot be trained by literally anyone else in the world, because what we found was unknown to everybody. And we took and created a training and testing facility with software and certifications. Next, please. This is the first plaque we awarded, and Tom was pretty much correct when he said that increasing your outside air is going to increase your energy consumption. That is absolutely true, no matter what stage you are in. But what is the good part about the software and our patents is we actually lower energy costs substantially. So this building here, Guy Menzel, chief engineer at Rosemont O'Hare Center, we literally increased his outside air upwards to 30% beyond what he had, and we substantially dropped his utility cost rate. And how we did it was through optimization, which is going to be presented or for you to review at the end of this presentation. I have 80 slides on this presentation. There is no way I'll be able to get to every one. So what I did was I included all the math and examples to actually start implementing implementing a means to start lowering your energy utilities through gas and electric. Next, please. The software that we use, we're currently, as you see on the bottom of it, we've been developing this for quite a few years, and we've just launched the software. And what this software does is it actually takes the risk of fraud in testing and balancing, and it normalizes the testing and balancing industry, because it puts everyone that's doing balancing on a level playing field, where when they enter data, it's asking for other data that actually cross-references to make sure that what they are entering is in fact factual. And it it basically does all the calculations, not basically, it does all the calculations, it does the energy calculations. And when COVID occurred, we created a COVID compliancy sector in the software that is specifically testing HVAC systems for heat transfer, energy fluid flows. Now this test literally will challenge a system within 20 minutes. The goal is always to be within 20 minutes or less. And it doesn't matter if the system is 1 CFM or 1 million CFM, because of the process, because of tracer gas technologies and theories, psychrometrics, thermodynamics, we are able to literally dial systems in to within less than 1% of error, which now the buildings are finding out that it's completely a valid process, and the systems are now as energy efficient and optimized as they humanly can be. Next, please. This is just another example of the software. Now, we also have a BOMA section. We call it BOMA only because we have our in-house software team. We have 4 writers that are continuously writing software literally 7 days a week with overtime. And we have a BOMA section that allows BOMA, when I call it BOMA, it's free to building managers, building engineers, building owners, architects, and professional engineers. What it basically does is puts the project in your hands without having to be deeply involved, other than you could see the process that's happening in your building at any time of the day. And you could see when they were working on it, what data was put in. It's actually putting your contractors under a microscope that are doing the testing. Next, please. Next, Alex. Thank you. Alex, yeah, there you go. Again, this is just another sample of how the software looks. Next, please. And again, this is just showing how robust and deep the projects and software goes. Again, there's COVID compliancy section, there's a energy section, there's a testing and balancing, air and hydronics. It's really sectored in 3, but it's all encompassed in 1, and every section talks to the other. Next, please. The reason I bring this up is there is the issue with increased energy usage, increasing outside air. Currently, Commonwealth Edison has been in contact with me regarding possibly offering rebates using our process. And we are continually talking with them, and the representative by it's blocked, but I believe it's Clear Cell. They're out of St. Louis, Missouri. They're in the process of going through our programming and our testing to see if they can award the rebates for our process testing. Next, please. Okay, my goal with this presentation is bring more immediate added value to building engineers watching, the team watching now. Next, please. My approach is to let you walk away with something you can use in your buildings, as Tom mentioned, that is in real time, with providing you the logic and formulas and examples to help you implement them. Let me see if I can do something here. Testing and balancing always goes hand in hand with HVAC energy conservation, direct utility cost savings, and waste. When I say waste, we've dealt with a lot of balancing or setting up of systems or mechanical contractors not exactly putting it in per plans and specs or reporting as the system really is. And that's where the waste really occurs. That's where the biggest savings is. And that's why 399 has me teaching their apprentices and their engineers how to test and balance themselves, how to identify waste, and to tell if they're getting a good job if they're not doing the balance because it's on another contract. That waste is a 20-year waste. Your normal life of a piece of equipment is 20 years or 60,000 hours. Space, tenant comfort is obviously an important condition that we have to meet. Industrial processes and temperature control, infectious building control associated with life safety. So life safety was MRSA, TB. If you remember, we had the anthrax threat not that many years back, where it was the hot item at the time, and everyone was looking at their outside air intakes and how do we filter it and how do we control it and how do we move it up or keep it away from anyone trying to sabotage with the anthrax. That pretty much died off because it's no longer a buzzword, because no longer has it been an issue. So it tends to just completely not be thought of, kind of what happened with 911. A lot of people tend to forget. With this COVID epidemic, I don't think anyone's going to forget anytime soon. I've been all over the world, and not every place, but all over the world. And I've been to Asia, and they were, not because of COVID, they were wearing face masks and filters on their face years and years ago when I was there. Next, please. Testing and balancing is not just the adjustment of dampers or setting up of fans and pumps in relation to a project's plans and specifications. Testing and balancing is thinking out of the box, identifying potential engineering mistakes or oversights, mechanical installation errors, shortcomings while following them to a conclusion. Next, please. Testing and balancing is working with the building engineers to help get tenants, employees, and their visitors back into the buildings. I have a blank corner upper right. Visitors back into buildings during this COVID-19 pandemic, which maintains the revenue stream for the building owners, which is right now the most important thing for not only the building owners, but for the building staff. Everyone's leaving the buildings and not coming back. And how do we get people back in the buildings? That's really the priority, not only for the owners and building managers of the company or of the building, but it's also everyone that's on staff. If we don't figure out how to get tenants to return and new tenants to sign up and employees to come back, where the companies that have leases in the building, there's no revenue stream. And look what happened with a lot of the hotels. Look what happened with a lot of the movie theaters. They're shut down, and a lot of building engineers are unemployed along with other staff. Next, please. My whole goal, I'm going to jump off right now. My whole goal was really, as soon as COVID happened, to come up with a solution to get people back in the buildings. And that's when we did the plaque. The plaque is compliant with CDC, ASHRAE, World Health Organization, and OSHA. So this is the key that I want to get across. COVID-19 has changed how building operates. It increased operating costs with extra staff to maintain infectious cleanliness, costs for the chemicals and supplies, increased HVAC costs with UV, MERV, and ionization filtration, with the cost to increase a building's air changes per hour. It's a challenge for any owner to be able to absorb these costs that are constantly being hit by them or hit against them. And yet we don't have the revenue, the people wanting to come back in because they're uncomfortable to return to the buildings. This is what we have to change. Next, please. Priority of the buildings is getting back the confidence of building tenants, employees, visitors, prospective tenants to rent or return. Anyone returning wants the assurance that the building's management has done everything possible to meet the prescribed recommendations made by CDC, WHO, ASHRAE, and OSHA to make a building as safe as possible to protect them from the current COVID-19 pandemic. Buildings will need to maintain this label for years to come. This is not anthrax. This is going to hang with us for a long time. Now with the virus mutating and new levels are occurring. It's not going away anytime soon. Now, one thing to understand, CDC, WHO, and ASHRAE, along with OSHA, they tried to work together to come up with a solution in the very beginning when it was really becoming public, March, April, February. They worked together. They came up with a lot of ideas to try to mitigate damages and keep the buildings up and running. The filters, so everyone knows, the filters, the main logic between the filters actually came from OSHA. And because OSHA does a lot of filtration testing, ASHRAE, CDC, and WHO ran with that. The other filtration, the UV ionization, and the MERV 13, which is again a proponent with ASHRAE, OSHA and ASHRAE, they threw everything at the systems and buildings to quash this concern. We're going to get into it, and the next slides we're going to discuss the filtration a little more. Next, please. As mentioned in the previous slide, everyone who wants to return to any building is looking for the confidence to return. Majority of people have no idea what this confidence encompasses, with so many recommended remedies and minimal positive results. One thing we do know is that outside air is actually helping, and it doesn't appear there's a big risk when people are outside and there's a lot of natural air changes. COVID-19 hasn't slowed down. It's constantly breaking records with new cases and worse. Surface cleaning was the #1 priority when the pandemic started. It's been now identified the virus is passed primarily through and by respiratory means. Filtration via MERV 13 ionization and UV has been challenged as a viable solution. Each has either a shortcoming of their own or health risk and issues as part of them. Next, please. Go ahead, Alex. There we go. Steps to begin creating a legitimate, healthier building, interior environment, retro commissioning the building's HVAC, ventilation, heat transfer systems. Tom already touched on that. Going back in and what he was discussing, going back in and actually looking at how we're operating, how we're filtering. Identify actual HVAC system fluid flows, heat transfer, and energy consumption. Incorporate ECMs, or energy conservation measures, which represent the greatest energy efficiency and lowest utility operating cost. Optimize the building's HVAC heat transfer systems to within equal to or less than 1% of error. This is being done. Increase the outside air ventilation rate without losing building comfort and energy efficiency. The error is actually quantifiable now, and increasing the outside air and not increasing utility bills can absolutely be done, providing you optimize your systems. Next, please. Testing and balancing encompasses adjustment of fluid flows. We're getting into the balancing now. Testing and balancing encompasses adjustment of fluid flows, the full understanding of energy conservation and optimization. Testing and balancing is responsible for reducing the building's watts per square foot, heating BTUH per square foot, and reduce kilowatt hours and therms build. Next, please. This is CEAC. Have you rated your building? Ratings are based on a square footage basis and normalized for the type of building you have. Most people are aware of CEAC and have challenged their building to see where they stand per square foot, and basically, where do you rate? Next, please. According to U.S. Department of Energy, the average number of kilowatt hours per square foot is approximately 22.5 kilowatts per square foot. The average cost of utilities for commercial buildings is $2.10 per square foot. Now, that is obviously an average nationwide. If you're in Florida and a lot of mechanical refrigeration, air conditioning, it's going to be a little higher. If you're in Minnesota, Alaska, it's going to be a little lower. Your gas utilities are going to take over there. Next, please. Let's get started understanding the first steps of testing and balancing. where we can start saving money. Next, please. Testing and balancing air and hydronic systems start off with ensuring systems, balancing dampers and valves are wide open. Go through the system, read it out, and make sure everything is wide. Go ahead, Alex. Go ahead and make sure everything is wide open. This prevents your systems from having adverse effect of system static and hydraulic head pressure. We don't want to start balancing a system where all the dampers or hydronic valves are partially or fully closed, because we want to have the least amount of pressure against the system while we increase flow. You're going to see a slide. Pressure and flow together is extremely expensive. A fan with no pressure barely costs any money to operate. A fan with no airflow but high pressure is, again, very cheap to operate. But combined, that's when you start spending money, same as with pumps. Next, please. The term box, I'm going to use box in this presentation quite a bit, and the building engineers understand the term box when we talk VAV, fan-powered CAV boxes. The acronyms for variable air volume and fan-powered box will be universally used throughout this presentation. Referenced as either VAVs or fan-powereds directly, or simply described as box for shorter means of reference. Now, this is anytime you hear the word box through the presentation, we are talking about a VAV system where a lot of energy savings can happen immediately. The term box is universally accepted in the HVAC industry when used in context with context and discussing VAV and fan-powered box systems. Next, please. Let me grab a water. Next step is to read out the air and hydronic systems to find the sum of the total system fluid flows and compare it to the sum of the required flow. So we open up the system completely. We go through and we use a flow hood to go ahead and read out all the air flows, or maybe we'll pitot traverse our system to get total system flows. And for hydronics, we'll go in to each circuit setter. We'll read each terminal to see what each coil terminal device has for hydronics flow. And we'll compare that with the pump, doing a pump Loctite to find the pump impeller size, and then a full flow test across the pump to identify full flow on a pump curve. The key here is, and this is the most important thing that you need to get in your mind when you are doing testing and balancing. It's a key terminal, and that terminal is either a diffuser, the terminal is either a hydronic coil circuit setter, and also we're going to use boxes, VAV fan power boxes, and put them into the terminal technology, and the thought that we have to know what the least flowing device is on any one system, be it a VAV, outlet, or coil. Next, please. The system's least fluid flowing terminal, along with the system's least fluid flowing VAV fan power box, would be considered the key terminal and key box. So if you have a constant volume system and we're on the supply, you're going to have one key outlet. And that key outlet was the one that was flowing the least amount of flow. And there will also be a key outlet on the return side of the system. Those are the two key devices on a supply and return that you could literally remove the dampers to, because everything gets balanced to these least amount of flowing devices. Now, every VAV will have a key diffuser on the VAV or fan powered box. So if a VAV is VAV1 is feeding 4 diffusers in the laboratory, one of those 4 diffusers is going to be wide open. We just don't start balancing and having all dampers partially closed. They all start wide open, and then you find out, again, this key outlet, and you make sure it stays wide open. You proportion balance into that diffuser. This is going to be explained in the next couple slides. The next VAV number 2, which remember you have a key outlet on the first VAV number 2 feeding the lunchroom, it will also have a key diffuser, and it's feeding 6 grills. So if you can understand what I'm saying, every system in a VAV is considered a separate system from the air handler, a branch of, but it's separate from the air handler that is controlling and conditioning one space. So what I'm describing here is an example of a terminaler box with 45 CFM actual versus 50 CFM required. That's at 90%. We'll go 47.5. That'll be 95%. A terminal box with 180 CFM actual versus 200 CFM required is 90%. My point with this one, because 45 from 50 is actually 97.5, 95%. Because the flow is low, do not look at that as the key. It's the percentage of actual flow. 90%, the 90% terminal flowing 80% or 90% was my example here. Next, please.
We do have one question that came into the chat.
Sure.
If I could interrupt you for a minute. How do you work with various BAS technicians regarding K-factor setting adjustments?
Well, the testing and balancing technicians. Okay, so you're talking K-factors. Ask it again. I think the gentleman or lady's talking K-factors of a diffuser, not of a box. Could you ask that question again, please?
Sure. How do you work with various BAS technicians regarding K-factor setting adjustments?
Okay, K-factors could be used as terminal devices, but because you said BAS, building automation system, I'm going to assume you mean the ones when you're adjusting, because you're BAS, you're adjusting, then I would assume a VAV system. The K-factors are to be found by the balancer, and that could be the building engineer with a flow hood himself or a pitot tube. And the K-factors, it could be either the square root or a simple division K-factor. It's dependent on the software that's being used. You have Johnson Controls, Siemens, and how the K-factors are actually changed. They're pretty intuitive now, where you can actually say, the box thinks it's flowing 500 CFM. The balancer reads an actual of 420. There's some programs that you can actually enter 420 actual, and it will all automatically change the K-factor. The big thing with a K-factor and what is not done, and where the BAS and control guys make a mistake, is everyone goes off the blueprints and they'll look at the inlet size of the boxes, the neck size of the boxes. They'll say it's a 10-inch box, a 6-inch box, and they will run with that factor. The most important thing is doing a VAV system and balancing a VAV system, validate what size inlet neck you have going to that box, because that is going to drastically change how the box responds. Because if it thinks it's a 10-inch box and it's actually a 6, it's going to respond very adversely and not fluidly change for you where you think you're going to be. So as far as K-factors, that's an open question that really can't be answered because the BAS technicians that we work with, be it train, they work direct with us, or we input the K-factors in ourselves. I hope that answered it. Okay,
Thank
Alex.
you.
The process on how to calculate motor brake horsepower is in a later part of this presentation. Let's say you have to increase the airflow on a system. Should increasing the fan or pump motors be necessary? You will calculate the fan or pump motor's brake horsepower. That's the first thing you want to do. You just don't want to start increasing flow without actually knowing what the fluid, what the actual available brake horsepower is. We don't want to have a 30 horsepower motor in there and we're operating at 29.5 brake horsepower and just start adjusting a pulley or changing pulleys and going past the nameplate rated horsepower. or the installed heaters, breakers, fuses on any one system. So you basically want to read your airflow and then immediately calculate your brake horsepower for the system you just read those hydronic or airflows for. Next, please. At this point, you would go to the system's HU fan or fans, pumps, and make the necessary adjustments, increasing or decreasing fluid flows to begin setting up the primary fluid moving devices. Now, if we are decreasing flows, we probably aren't too concerned at that moment with the actual operating brake horsepower, because we're going to slow it down. So we know we're not going to increase the load on the motor, but it doesn't mean the motor wasn't operating over brake horsepower, rated nameplate horsepower, but it's the safer move that you can do. When we're talking about making adjustments, a lot of your engineers will say plus or minus 10%. You have to realize that that's a big number. So what I mean by this, who aren't involved with testing and balancing, if you have a fan system rated for 10,000 CFM and it says, go ahead and adjust that fan system plus or minus 10%, I'm allowed to move below 10,000 by 1,000 CFM. I can set that fan up between 9,000 and 11,000 CFM. I like using tens just for ease of math. So again, we have a 10,000 CFM fan. We drop it down to plus or minus 10. We're allowed to drop it down 10%, 9,000. So what's the big deal? Well, it's a huge deal. So what will happen is the heat transfer will take 11% longer to actually condition the space than if you actually had it near 100% mark. If you take 100 divided by 90, the sum is 1.11, 111%. And that means that, okay, I'm going to jump here. A lot of people like to operate and think they're saving money by slowing the fan down. But reality, if you have a chiller system with VAVs and pumps, you have a simple thermostat or temperature sensor, just like your house. What dictates how your system operates, heating or cooling, is your thermostat. Your thermostat dictates how often it runs in the summer, how often the furnace runs in the winter. The same in a building. You have a chiller at massive amps, and you have a simple thermostat that needs to be satisfied. So there's usually an air handler with a supply and return fan feeding the space with the sensor that also probably has pumps circulating water flow through the coil, chilled or hot water. You then go and take that chilled water and you have secondary pumping systems. You might have had a tertiary system, secondary pumping systems, flowing water, that's horsepower. And then you have your primary pumps at your chiller. Again, we have horsepower. Then you have the chiller itself and additional pumps sending condenser water to the tower and the fans on the tower themselves. So you have a lot of energy usage. And if you can't satisfy the sensors, you will operate at 90%, you will operate your equipment 11% longer, just because simply you were going to go ahead and let a 20 horse motor operate at 90%. Next, please. Typically, you set a fan system deliver plus 5 to plus 10% fluid flow, CFM as compared to required CFM flow. The system will slowly cascade down in terms of total fluid flow being delivered as you begin converting system fluid flow into system static head during the balancing of your terminal devices. You're going to lose. My point here is you're going to set up for a plus 5, 10% at first. You say, well, Lance, I thought you're trying to save energy. My point is, as you start dampering fan system diffusers, you're building up static head. You can't help that. And that static head, that CFM that you cut down 100 CFM at one damper. It does not mean you gain 100 CFM proportionally through other diffusers. you may lose 15, 25% of that 100 CFM. It gets converted into static. So you have to, if you start at 100%, you'll probably end up in 95, 90% when you're done. And you have to speed it up anyway. We found over time, start with the system wide open, adjust your fan to equal +5 to +10% airflow, and start your balancing at that point, and you will cascade. You will slowly lose that high percentage, and you will actually proportion balance the system into itself via flow and pressure wise. Next, please. Hydronic pumping system is a little more exact, and there's not the duct leakage. With airflow, when you're balancing with airflow, you have duct leakage. You clearly shouldn't and probably don't have hydronic pipes leaking, because you would see them in the ceiling. No one's identifying the leakage in duct systems. So that +5 to 10%, part of that is losing airflow into the ceiling because its ducts were not sealed proper. Pump systems, a reasonably good pumping system, we will go 2.5 to 5%. Now that's a guess. If there's not a lot of terminals on the pump, we'll probably go with 2.5% or less. If there's 30, 50 terminals on the pumping system, we'll probably go near the 5%, keep balancing, convert that into hydraulic head, and end up close to the 100% design flow when we are done. And again, we converted flow, GPM, and hydraulic head into a one unison flow and pressure on the system as a whole. Next. It is recommended you understand a specific type of balancing style, which is called proportional balancing. Proportional balancing is what, if no one's balanced before and they're looking to balance systems, it's really what you should do. Proportional balancing is taking and reading out all those diffusers we talked about, be it 10 or 100, be it even 2. Proportional balancing is identifying the key outlet, and then that key outlet is the one that the next lowest terminal device, next lowest diffuser gets balanced into. So if that lowest diffuser, lowest terminal device is at 50%, there's 10 diffusers, we'll say, 10 terminal devices, it's at 50% of design, and the next lowest one percentage-wise is at 60%, you won't balance that next terminal at 60% into the 50. You'll assume that 50% will come up a little bit. You may drop that and shoot for a number of 61 to 62% of design on that second device. And then when you go to the third, you might shoot for 65%. And then when you go to the fourth, it could be something well over design, and you might be shooting for a 70%. But when you're done, you don't have to go back and rebalance damper into damper, diffuser into diffuser, terminal into terminal. When you're done, you simply read it out and you record your flows. It's really a one-pass balance that works really well. It's explained in the test and balance manual offered by 399 during training. If you take the testing and balancing class, and it's a good reference to have. If you don't have access to the manual, it's something that you would want to look up on the web or YouTube. Next, please. Okay, watching my time here. It's considered ideal to do its proportional. It's considered ideal due to its proportional rewards and limited number of times you must visit each terminal device, which I talked about. It does have its pitfalls. Rogue terminal devices, if you have a device that is at 20% and it has let's over exaggerate, a 2-inch duct going to it and it needs 1,000 CFM, you don't try to balance into that. You let the rogue terminal stay where it is and get the contractor to fix it, replace it, but remove it. Next, please. Check your system's fan and motor components. Identify if the motor and fan pulleys are in good shape. Don't align with anything else than a laser. Check that the belts are not excessively worn, cracked, and when you have adjustable pulleys, they're only for balancing at startup, replace them with fixed pulleys, and you will have belts that can last 10 years. Absolutely last 10 years. Next, please. Check your system's filters. As you read through this, a nice thing to do is actually, as you're sliding filters, the box type filters, as you slide them in, throw a piece of masking tape between the seams and hold them together and slide them in. It creates, it eliminates blank off. And when you have to remove them, you grab the first filter and they all follow right behind. And then check your expanded metal, OA and exhauster, make sure they're not starved. Next, please. Look at your OA-RA exhaust air dampers. This is so important. If the OA is at 30%, your return should be at 70% visually. If your RA is at 50%, your OA should be at 45. It always has to equal 100% or you're starving your system. Next, please. Time flies. The adjustable pulleys we talked about, they're for initial balancing. Here's a formula I gave here. If you want to calculate after you do a test and balance on a system or want to change pulleys, use what I have there. Fan RPM divided by motor RPM times fan pitch diameter. When I say pitch diameter, I'm meaning the stamping. Use the stamping on the fan. It's usually there. Usually you can't see it on the motor, but the fan you can. It may say 3B 58 by 1 1/2. Well, the 58 means 5.8. 3B 300 by 2 inch. The 300 means 30 inch. Clearly, you're looking at the pulley and you can tell it's not 300 inch, it's 30. And what you would do is take fan RPM actual divided by motor RPM times the 30 inch. You would actually know what your motor was operating at. The motor PD of that pulley was operating at. Next, please. This is explaining that you want to know increasing your motor pulley increases fan RPM. But here's a good one to remember. If anyone tells you that a motor shaft is 5 3/16, 1 7/16, it's not. They measured it wrong. Motors are never in 16ths and fans are never in eighths. You can have a motor shaft that's a 1 inch and you can have a fan shaft that's a 1 inch, but you will never have a motor shaft that's a 1 1/16, and you will never have a fan shaft that is 1 1/8. So try to remember that. If you take measurements or if your technicians take it, don't realize there's an issue if they inverse the two. Go ahead, please. Record nameplate rated motor amps, final motor amps, volts, motor starter information, motor fan RPM, filter and belt quantity and sizes, fan system components and static pressures as a final, and actual fluid flows as compared to design. Next, please. Let's jump in energy savings, which I love. Okay. We don't unfortunately have a lot of time left because we have a question and answer period. Alex will let me know when I need to stop because I have to answer questions. But this is where I saved the majority of money for One O'Hare Center. We simply optimized all their equipment. We increased their outside air 30% more than what they were operating with. And we substantially dropped their utility rate or utility billings an excessive amount. And I'm not at liberty to be saying what they dropped, but if you wish to call Guy, I'm sure he'll tell you. It was substantial, and the return on investment, doing these ECMs, energy conservation measures, using the software, what is the return on investment? What is the simple payback? What's a simple MAR, minimum attractor rate of return? It's usually within 1 to 3 months. Everyone's happy with the 3 to 5 year, even 7-year payback. The architect of the state, which is Washington, D.C., they accept a 30-year. Equipment only lasts 20 years. They're happy with a 30-year return on investment. Doing what I'm talking about in this slide will save you so much money, and you can start it right at your computer. And then you'll never leave your computer. Next, please. Pulse width modulation, VFD, simply don't confuse the two. They're both the same. It's semantics. They're exactly the same. Next, please. I have written down the formulas in this presentation for you. If you follow my leads through this presentation, it literally directs you how to go ahead and calculate energy savings and how to, again, literally sit at your BAS CPU and adjust your VAV system up and down. Never leave your chair, never leave your computer, up and down, and save substantial money. You say, well, how am I going to save money if I ramp it up because I'm short static? You'll save money because your chillers, your boilers, your pumps will throttle back and throttle off sooner. You just can't look at increasing a fan RPM as immediate cost. You have to realize when a sensor, a thermostat gets satisfied, it's shutting down more than just, or slowing down more than just one motor slash fan or pump. Next, please. How are we going to save money? Naturally understood. Again, slowing a motor down saves money. Next, please. Okay, this is the powers of three. It's simply, that's all we're doing. And what I'm going to demonstrate here is we slow a VFD down from 100% speed to 80%. And my question before we go to the next slide, if we slow a motor down from a 100 horse motor down from 100% to 80%, are we going to, and it was at full 100 brake horsepower, are we going to operate at 80 horsepower then? If we slow from 100 at 100 brake horse down to 80%, are we going to be at 80 horsepower? No, we're going to be at 51.2 horsepower. Same with the 10 horse motor. From 100 to 80, you will save almost 50% of the kilowatts, watts/kilowatts used. That's the magic of VFDs. Next, please. I'm using the 100 horse that I talked about. I like using hundreds and tens for ease of understanding. Next, please. So this is the formulas. This is what we do. First, if you remember, I talked about calculating brake horsepower, and I will again. This is the slide. Let's think Mike Singletary, number 50. It's just ironic, it is 50. That's the brake horsepower formula that you would use to calculate brake horsepower of a motor. A lot of times you will not have power factor or efficiency. You'll see under rated volts and amps, there's a efficiency and power factor. Many motors is missing one or the other. You can't do it, or both. The next formula down below that actually eliminates that deal, and it actually calculates a factor for that motor, and it actually is more accurate. Their formula brings them to 99.31 using their data, and I actually bring it to 100. Manufacturers say close enough. I say let's get exact, and that's the motor nameplate to the right. Next, please. So this is the start of how to save the money. Let's look at a typical schedule, and this I call it COVID-19 schedule. But what's it cost to operate? What's it cost to operate that motor at, or any motor at 100%? This is the same format you will use for any motor in your building. You're going to convert your motor first into amps, or I'm sorry, watts and kilowatts. That's the purple formula. Set up your schedule, get an idea what everything is. You're operating at, in this example, down below the building schedule, I have 3,952 hours. And then I take my kilowatts per hour, times, I just use 10 cents. I like using 10 cents. If you say I use 8 cents per kilowatt hour, take that number, 35,265 times 0.8. If you're at 12 cents an hour, take $35,265 times 1.2. So 10 cents is an easy number, and you adjust with your actual utility rate accordingly. The average motor life expectancy is 60,000 hours. So if we take that 60,000 hours, and if we did have a schedule like this, we'd only operate at 15 years and we'd be looking at a new motor. We know that normally we get 20 years out of our motor. It really doesn't matter. It's not going to change the cost of operating this motor. cost to operate that 100 horse motor at 100% without optimizing your system, your VAV system, is $35,265 a year, and total life would be $535,000, a little over $500,000, the life of that motor. Next, please. Now I'm going to take it down to 80%. You see the power of 3 there. I'm going to go from 60 hertz, 100% speed, down to 48 or 80% speed. Doesn't matter. 60 times 0.8 is 48. 100 times 0.8 is 80% speed. You simply take the VFD, drop it down to 80%. This is what's going to happen. You're going to drop your brake horsepower to 51.2%. If it was a 10 horse motor, you're going to drop it down to 5.12 brake horsepower. It doesn't matter. That's the cube of that sum. What savings will we have? When at 100%, at 60,000, we're at 35,000 at 535. Reducing down to 80% is 51.2 annually equals, what am I doing there? Reduced operation 80% at 51.2 equal annually at times 0.512. We will drop from 35,000 down to 18,000 annually. And we will take the 60,000 motor life hours of 535,000, $500,000, and drop it down to $274,000, $250,000, little over. We're going to reduce the cost basically just slightly over half. And that's facts. That's exactly how a VFD operates. And that's the savings you can realize. And we took the freak drives down in many buildings well under 80% because they had no idea what they were operating at or where they should be operating at. And I'm going to get into that here for you. And Alex, again, you let me know. Next, please.
We don't have any questions currently, so if you do have a question, please put it in the Q&A or chat. Otherwise, Lance, you can go ahead and wrap up this topic. You have
Okay.
a couple more minutes.
Gotcha. I have 3 more minutes. I'm watching. Next, please. And then again, I show I reverse it around. I show how much you'll save annually. I showed the cost prior at 18,000 annually. You'll save 17,209, and you'll save 261,000 from the 535,000 you're operating at. Next, please. If we had a 10 horse motor, I already gave you the answer, and we reduce it by 20, what would we operate at? 5.12. Next, please. Next, please. I'll go through these fast. This is showing additional reductions at 5%, 10% reduced VFD operation. Still can use the same percentages. Next, please. These savings can be happening today and primarily begins with the BAS system. I'm going to walk you through in this slide. You simply follow what I did in my slides at your BAS system. It's clearly explained. Next, please. I realize how close I am here. Savings found in the BAS system. We can fans and pumps pressure only. Okay, we're going to get into what pressure and flow equals. Next, please. We're going to breeze through this. This shows, and it's at the lower left of that white page shows, forgive what I'm going to say, but it's called big ass fans. Many people know what that fan is. You'll see 100,000 CFM fan on that same sheet is operating at 1 horsepower. So all kinds of CFM at only 1 horsepower, but it's really just dispersing airflow. It can't create static. We might need a much bigger motor. Next, please. And this is a high pressure fan that can operate at 10 inches of pressure to the left at 1 horsepower and only move 323 CFM. Point. You're moving well less than 100,000 CFM and well over 1 horsepower. It's pressure and flow combined that costs you money. Next, please. We have 20 slides left. How are we going to save money with our set points and sitting at the BAS system? Great question. Next, please. you need to read through this. You need to actually go through and read this and go point to point. I'm going to briefly explain what the slides are. This is actually sitting at the BAS system and probably cutting your energy usage at most of your building engineers' buildings. I could easily say 20%, just sitting at your BAS system. Nobody knows what their set points are. So here, how did you come up with your static pressure set point? Here's a normal. It's the previous set points given by another building engineer, given by the design engineer. He could never know that. Set points that was done at a like building like mine, so we're operating at the same static pressure set point. These are all wrong answers. You find out specifically what the static pressure is, and that's what you can do at your BAS system. Next, please. This is the two that should have done it. Either the test and balance contractor would have said, here's your static pressure set point, and here's your key box, the one that's having the worst time producing flow, or your in-house building engineer yourself can find it out. Next, please. This is the process to go through it. You're looking for the worst case VAV box. So when you call everything wide open, not wide open under control, delivering flow, you have to go through and look at your box damper positions, and you find the ones that are, well, you find the one that's most wide open. If a lot are wide open, you're not operating enough static, or the box isn't balanced properly. If you have boxes that are operating at 85, 90% and still have 10% to go, you have huge energy savings coming your way. Next, please. This is continuing the process. Next, please. It's detailed, and you'll have my phone number. If you have questions, you can call me and I can walk you through it in your building. This is, again, calculating. I tell you to gather your watts, brake horsepowers. Let's find out what kind of let's find out what kind of energy you save. Next, please. We have 13 more slides. This is filters. I'm glad we're getting into this. Understand that MERV 13 can only trap 0.3 micron. The COVID virus is 0.1. So the MERV 13, it's better than nothing. Absolutely, I'd rather have a MERV 13 than something less than. And a MERV 13 is a good filter. And the reason they picked that is there's not a huge static drop across the filter, which means it's not as finite of a filtering filter. So they're trying to save money and filter at the same time. MERV 13 is equal to a chain link fence and having a handful of ping pong balls, throwing it at the chain link fence. Majority of them are going to go through. A couple will stop. Next, please. This is the example. Now they're talking from 0.3 to 1 micron. It's 50% equal to or less than efficient. Well, they get to use, it's called bins. They get to use from 0.3 to 1. And then they look at the efficiency. The mass majority efficiency was towards the 0.1 micron, not the 0.3. And your COVID is at 0.1. Next, please. A MERV 20 will stop the COVID virus, but the velocity going through it has to be down to 50 feet per minute. Your air handler has to be at 500 feet per minute to continue moving the amount of heat transfer you need. So your filter bank would have to go to approximately 10 times the size it is already, and you don't have a fan that could draw through what basically is trying to push air through a brick wall. But that will actually, that's the only filter that will stop the COVID virus, and that's only going to be found in military facilities, pharmaceutical facilities, which can afford to do that. Next, please. Here's the RGF, the ionization. Everyone went and started running with ionization. RGF, bipolar, all these terminologies are really just the manufacturers. But this page right here clearly states we have no proof that it will kill the COVID virus. We simply believe it will because it killed other types of items before, but it's absolutely not tested nor proven to kill the COVID virus. And the issue with ionization is ozone. And ozone is absolutely damaging to your respiratory system. Next, please. UV lighting, this is from University of Minnesota and another facility. UV lighting absolutely is capable of killing the COVID virus, but we have to realize, remember I said the 500 feet per minute, we have to realize that the airflow going by the UV is moving at 500 feet per minute. And go to the next one, please. And to realize that 500 feet per minute is not going to effectively allow it to be killed in the airstream, because UV takes power, the wattage, distance the COVID virus is from the bulb, and time, how long it sits and sunbathes in the UV lighting will determine its kill effectiveness. But ripping by it at 500 feet per minute, it's not viable. Having it wash the filters where that was caught is a good thing to have, but it's not a cure-all for a ventilation system. Increased outside air is flushing of a building, air changes. And that's only done with outside air. It's not done with a 100,000 system moving 100,000 CFM with only 1,000 CFM outside air. That is your effective air change rate that you use, 100 CFM, not a 100,000 CFM supply return system. Next, please. 7 more slides. This is continued UV lighting for you to read. They really don't have the bulbs nor the power to actually do what is needed right now, but it's not a bad thing to have if you're going to bathe, again, filters or coils, but it's not going to mitigate the whole problem. Next, please. This is simply for you to read. The N95s is pretty similar to the MERV 13s filters. That's all I want to I put this in here just so you know, now that you understand the percentages. It's effective at 50% or less at 0.3 micron. Next, please. Next 3 is compacted with data. Next, please. Okay. You want to go through and troubleshoot your building? Use a rule of thumbs. The trusted rule of thumbs are 1 CFM per square foot and 400 CFM per ton. Constants, there's no give in these constants. 500, 12,000 BTU per ton, and 15,000 BTU per ton. Constants with give are 2.5 GPM per ton and 3. And the give means if you increase your chilled water, then you're going to decrease your delta T, but it still has to maintain 12,000. So there is give in the GPMs and delta Ts, but it still will always equal 12,000. That cannot change. And the reason we have 15,000 BTU condenser, we have heat of compression, heat of rejection, we have bearing heat, motor heat. You do not have your condenser, your cooling tower. If you have a 100-ton chiller, you have 100 ton times 1.25, you have 125 tons of heat rejection. 15,000 divided by 12,000 is 1.25. You have 25% more BTU being rejected than by what was absorbed, because you have to get rid of heat of compression, bearing heat, motor heat. Next, please. Okay, so I take you through a 10,000 square foot space. I note that you read 8,100 CFM. That's 8.1 CF, or I'm sorry, less than 1.81 CFM per square foot. You read 53 GPM. Chilled water, that is conditioning space, is 61.5 GPM. Condenser water to remove the heat from the space. Next, please. This looks ugly. I took the constants from the previous slide, put them up there. I took the facts of the space at 10,000 square foot. I said to next slide, let's do the math. I take 10,000 divided by 1 CFM per square foot. So we have 10,000 CFM required. 10,000 divided by 400 CFM per ton. We have 25 tons required cooling. We have then 25 tons times 2.5, we need a total of 62.5 GPMs chilled water. 25 tons times 3 GPM heat of rejection, we need 75 tons. I then state in the next section down, we had 10,000, we read actual 8,100, it equals a deficit of 1,900 CFM divided by 400 CFM per ton, you're short 4.75 tons. times 12,000 BTUH per ton. I'm 4 sections down, 57,000 BTUH. I did the same for the chilled water. I did the same for the condenser water. Now here's the point. The very bottom line, the space will operate at best using the largest deficit, 25 tons required minus 4.75 tons, which is based on the CFM actually read, minus will equal 20 and a quarter tons, 81% of design. Now take 100, your design, divided by 81, whatever that comes up to, that's how long your system will have to run. It will run that much longer to satisfy the sensors, thermostats, et cetera. You will pay dearly if you don't get your systems optimized. Next, please, 2 more slides. Any questions? And then obviously the last slide is my name, phone number, if you need to reach me. Go ahead, next slide, please. Thank you, Alex. Any questions or no?
We have no questions at this time.
Okay.
Thanks everybody for sticking through us. We ran over a little bit extra, but we will be sending out this full presentation and a link to the recording too. So you can rewatch this and help, Lance can help you get through it if you're running the calculations. We'll also include his contact information in case you'd like to reach out to him directly. And now I'll turn it over to Tom to wrap everything up.
Lance, thank you very much. And all participants that stuck around, actually looks like just about everybody did. So good stuff. And Lance, I know that you were trying to clear up some of the misinformation about the one size fits all to remediate the COVID virus. But as you pointed out, that there's probably a lot of things that we have to do inside our facilities to help mitigate it. So, but thank you very much for sharing all your calculations and your insight.
Thank you.
Today. And just a heads up for next month, in February 17th, we'll also provide another educational webinar with ComEd as the presenter. So hopefully we'll see you all next month. And thank you very much, Alex, for running us through the PowerPoints and assisting Lance. So we'll talk to you all soon.
Thank you all. Thank you all. Thank you.
Thank you.